Today we're going to talk about the surface area of a surface of revolution, a surface created by rotating a curve around an axis, such as the x-axis or the y-axis. So the formula for the surface area, if we rotate a portion of a curve y equals f of x between a and b around the x-axis, the formula for the surface area, which we'll discuss later where this comes from, is this. It's the integral from a to b, 2 pi y, the square root of 1 plus dy by dx squared dx. So let's take a look at an example. Suppose we take a little piece of the circle y equals root 4 minus x squared for x between minus 1 and 1, and we rotate it around the x-axis. Then we get a shape like this. It's like a piece of a sphere where we've cut off the two ends. So the surface area of this should be given by this formula here. So let's do this calculation and see what we get. So the derivative using the chain rule turns out to be minus x over root 4 minus x squared. So the integral we need is the integral between minus 1 and 1, 2 pi y, root 1 plus dy by dx squared. In this case, when we substitute in for y, that's root 4 minus x squared. Substituting in here for the derivative, we get square root of 1 plus x squared over 4 minus x squared. This appears to be a complicated integral, but in fact it simplifies considerably. The first thing we do is we put the thing inside the square root over a common denominator. And so that means that we write the 1 as 4 minus x squared over 4 minus x squared. And when we do that, you see these x squareds cancel out, leaving us with a 4 on the top and a 4 minus x squared on the bottom. So now the root 4 minus x squared on the bottom will cancel out with the root 4 minus x squared here. And that'll leave us with just a root 4, which of course is 2. When we take the integral from minus 1 to 1 of 2, we just get 4. So our final answer is 8 pi. Let's have a look at another example, this time a little bit more complicated. Let's look at what happens when we rotate the curve y equals e to the x between 0 and 1 around the x-axis. Again, a fairly straightforward example. But unfortunately, as we shall see, the calculations become pretty tricky. So here's our formula. The integral from 0 to 1, 2 pi y is 2 pi e to the x. And the derivative of e to the x, of course, is e to the x. When we square that, we get e to the 2x. So we get this integral. We have to integrate e to the x times root 1 plus e to the 2x. Now, normally, probably you would do this in a couple of steps of substitution, but I'm going to do it all at once to speed things along. So I want this is 1 plus e to the x squared. In the spirit of trigonometric substitutions, I want to convert this into a 1 plus tan squared, which will then become equal to secant squared, and we can take the square root. So what I want is for e to the x to equal tan theta. So I can just make that substitution because that is the substitution theta equals arctan of e to the x. But we'll write it as tan theta e to the x because then when we take differentials we get secant squared theta d theta is e to the x dx. Then we also have to change the limits. So theta at 0 is arctan of e to the 0. Arctan of 1 is pi over 4. And theta of 1 will be arctan of e to the 1, arctan e. finally, this term, the root 1 plus e to the 2x, will be 1 plus tan squared theta, which we know is secant squared, and when we take the square root, we get secant theta. The e to the x dx we can replace by secant squared theta d theta, and we'll take the 2 pi out the front. So we've converted this integral into the integral of secant theta, secant squared theta d theta, with these new limits. Of course, that's just the integral of secant cubed theta d theta. And now we'll just recall what the antiderivative of secant cubed theta is. This is one of the classic integrals we considered when we were looking at trigonometric integration. So the integral of secant cubed theta is 1/2 secant theta tan theta plus log secant theta tan theta. The 1/2 cancels out with the 2 at the front, just leaving us with pi times that quantity, which we need to evaluate between pi over 4 and arctan of e. So of course, when we evaluate tan at arctan, we just get e back. Now secant of arctan of e is root 1 plus e squared, something we can either see using this algebraic identity or by looking at a triangle. But anyway, so this, since secant of arctan of e is root 1 plus e squared, the first term becomes this, and the second term becomes the log of e plus root 1 plus e squared. And then likewise, when we evaluate at pi over 4, secant pi over 4 is root 2, tangent pi over 4 is 1, so we get minus root 2 minus log root 2 plus 1. And that's our final answer. So not a particularly simple or straightforward answer, but in this particular case, we can get a closed form answer for this. Obviously, as you can see, as our functions get more complicated, this calculation is going to get extremely difficult, if not impossible to do in terms of elementary functions. Moving on, let's consider the case where we rotate the curve about the y-axis. So in this case, the area of the surface generated is the integral between a and b 2 pi x times root 1 plus dy by dx squared. So the only thing that's changed from the previous formula is that we now have an x in where we had a y before. So when we rotate around the x-axis, we need a y there. When we rotate around the y-axis, we need an x. So let's apply this to find some general formulas. We'll start off with the surface area of a parabolic dish. In particular, the parabolic dish that we get by rotating the curve y equals x squared from 0, 0 to root bb around the y-axis. And the reason I've chosen this for the endpoint is because I want to consider a parabolic dish of kind of height b. So from the y-axis point of view, the parabolic dish is kind of vertical and it's of height b above the x-axis. So putting this into our formula, notice that these limits are x limits, so we're going to integrate from 0 to root b, 2 pi x times root 1 plus the derivative squared, which is, derivative is 2x, so this is 4x squared. Now we have a fairly straightforward substitution. U equals 1 plus 4x squared, du equals 8x dx. We plug all this in. The dx changes. The x times dx gets exchanged for 1/8 du. The square root here gets exchanged for the square root of u. Taking the 2 pi outside becomes pi over 4. Integrating root u gives us 2/3 u to the 3 over 2. And then we just have to evaluate between 1 and 1 plus 4b, because when x is root b, u is 1 plus 4b. So we get pi over 6, that's the product of these two things, times quantity 1 plus 4b 3 over 2 minus 1. So that's the formula for the surface area of a parabolic dish. Not particularly simple, but that's what it is. Let's have a look at another example of rotating around the y-axis. Let's find the surface area of a truncated hemisphere. And this one we'll set up from scratch. So we just imagine now a hemisphere of radius r that we truncate at height a above the ground. So how do we set this up as a surface of revolution? Well, we want to revolve the kind of cross-section of this hemisphere around the vertical y-axis. So the cross-section will be a circle of radius r, and we'll center it at the origin. So the circle, the curve we want to rotate is going to be y equals square root of r squared minus x squared. And we want to take it up to height a. So what's our bounds on the x going to be? Well, this length is going to be a part of a right-angled triangle in which the hypotenuse is r, the radius, and the height here is a. So this base is going to be root r squared minus a squared. So we're going to rotate the portion of the circle, y equals root r squared minus x squared, between root r squared minus a squared and r. We're going to rotate this arc around the y-axis, and that'll give us the truncated hemisphere that we were looking for. Now let's do the calculation. dy by dx, y is root r squared minus x squared. dy by dx, using the chain rule, is minus x over root r squared minus x squared. So this radical term becomes root 1 plus x squared over r squared minus x squared, using the same trick that we did earlier of putting it over a common denominator. The 1 becomes r squared minus x squared over r squared minus x squared. The x squareds on the top cancel out, giving us square root of r squared, which is r, and then we have a root r squared minus x squared on the bottom. So the integral now is the integral from root r squared minus a squared to r of 2 pi x times this radical term, which is r over root r squared minus x squared. And then again, a simple substitution, u equals r squared minus x squared gives us du equals minus 2x dx. So the 2x dx becomes a negative du, leaving us with a pi and r and this term, which is now root u. Well, since we have negative integral from a squared to 0, it's natural to change that just into flip the limits of integration and write that as the integral from 0 to a squared. Now what's that? Well, the integral of 1 over root u is 2 root u, so we get 2 pi r root u evaluated between 0 and a squared, which is 2 pi r8. So that's an interesting clean answer to our problem. Of course, remember, if a equals r, then we should get the surface area of half of a sphere, of a whole hemisphere, which of course we do because the surface area of a sphere is 4 pi r squared, and we would get 2 pi r squared. What's more interesting is that this is only a function of the height of this piece. And if we do a little bit more work, we see that however we slice it, the surface area will be just a function of the height of the slice, or the width of a slice. In particular, if we slice the hemisphere exactly halfway up between, well, at the point a equals r over 2, then we'll get two very different looking pieces of the hemisphere, one which is very cylindrical at the bottom, and another which is like a cap shape. But interestingly, since they both have the same height A, they'll have the same surface area. Quite a curious fact. So that's all the examples that I'll cover today. Let me just have a quick word, say a quick word about the derivation of the formula. I'll just give a very heuristic explanation of this, not too many details. So here's our situation. In abstract, we have a curve rotating around the x-axis between A and B. And what we're going to do, as we usually do at this stage, is to partition the interval up to, from A up to B, and then in some way reduce the problem to a more rectilinear kind of situation. So over the individual subinterval from xi minus 1 to xi, we'll replace the actual surface by this kind of little conical band. So pi minus 1 to pi will be kind of the piece of arc length that we used in the Riemann sum calculation for arc length. And this will be like a piece of a cone. So let's have a look at the formula for the surface area of that kind of shape. So if we have a cone that we truncate, and the base radius is R2, and the top radius is R1, and the slant height is L, then with a little high school level geometry, we can show that the surface area of this will be pi times R1 plus R2 times L. And what we're going to use this in the following form. If we take R to be the average of R1 and R2, that's R1 plus R2 over 2, then the surface area will be 2 pi times R times L. So we're going to use this formula to approximate that slice, that little red band here. So what are the radii? Well, this radius here at the end is yi, it's f of xi, and at the other end the radius is f of xi minus 1, which we'll call yi minus 1. So our formula from the previous page tells us that the surface area of this red band will be 2 pi, the average of these two y values, times the length of this line joining pi minus 1 to pi. Now, in our discussion of arc length, we decided that there was an xi star between xi minus 1 and xi in that little subinterval, such that this length was equal to root 1 plus f prime xi squared dx, delta x, sorry. Now, if delta x is small, then this average value of yi and yi minus 1 will be approximately f of xi star. The details of why we can make that approximation are a little bit more complicated, and we'll just glide over that for today. So let's just assume that's true. That means that the surface area of this red band is 2 pi f of xi star times root 1 plus f prime xi star squared times delta x. So our approximation of the total surface area will be the sum of all these red bands sitting over the partition of A to B. That means that our approximation of total surface area will be the sum I equals 1 up to n of these SIs, and as our partition gets finer and finer, this estimate will approach S. In other words, S will be equal to the limit as n goes to infinity of these approximations. But if we look at this limit, this is exactly the Riemann sum expression for the integral from A to B of 2 pi y 1 plus dy by dx squared dx. And so that tells us that this limit is equal to this formula. So that explains, at least heuristically, where this formula comes from.